Hello everyone. So today we're going to start on 11.5, which will discuss another technique into solving a non-homogeneous differential equation called Laplace transform. So Laplace transform is actually a very, I wouldn't say complicated, but it definitely is a technique that requires a lot of algebra to complete. But remember, the idea is that doing algebra is actually more preferable than doing integral. That's the reason. So I'll show you how this works. So let's say we're given a constant coefficient non-homogeneous differential equation in this form. Let's say ay double prime plus by prime plus cy equal to f. And let's say with the following initial condition. With initial condition, notice that because this is a second order differential equation, we're going to have two initial conditions. First one is y of 0 equal to some number a, and let's say y prime of 0 equal to some number b. So this type of question, when we have a constant coefficient differential equation, the order of the differential equation actually is not as important because Laplace transform can actually be applied to higher order differential equation. But we're most likely going to focus on mainly second order, just for simplicity reason. The key, however, to use Laplace transform is that we must have some kind of initial condition to begin, and the initial condition preferably to be at 0, which is what we're going to be working with. So in this case, what happened is this: we can use an alternate method to solve this equation. So instead of using undetermined coefficient or variable or parameter methods, we can actually use this Laplace transform method to solve this equation. So it's called Laplace transform. One of the nice thing about Laplace transform is the following. The main goal of this method is to somehow reduce solving this equation into just some algebraic process. And the reason why is powerful in the sense that an algebraic process can actually be programmed into a computer to do. While using other methods that require some kind of analysis, usually much harder to program, because you require the program to actually think in order to determine what to do. While this method right here doesn't require the program to think. It just have an outline method that will always work. So it's a little different, but it's from a programming standpoint become a lot easier to do. So the essence of this method is to reduce the process of finding the solution into some basic routine algebraic manipulation. And remember, the idea is that those algebraic manipulation is fixed. It always works as long as you go through the process. And because of that, it allows you to actually program a computer to actually do that without any analysis at all. So how did this Laplace transform work? So in order to do that, use this method, the first thing I need to do is define what is a Laplace transform. Definition. So what is a Laplace transform? So this is what Laplace transforms say. If for some real value, real or complex, maybe just say or, real or complex number S, an improper integral of the form of integral from 0 to positive infinity e to negative st f of x dx. Oh, actually, maybe we use t, f of t dt, converges to a function of s. And the notation for that is this: L square bracket f of s, then the function L square bracket of f of s equal to integral from 0 to infinity e to negative st f of t dt is called the Laplace transform of f. Now, I know if you look at the definition, it might seem like, okay, what is this? Well, the key here is to understand that Laplace transform is very much similar to like derivative. Basically what we have would be, you're not actually going to be using this definition to try to create Laplace transform. Just like when you first learn about derivative, you learn about the definition of the derivative, but you actually don't use that definition to actually find the derivative. We develop shortcuts that allow us to actually find the derivative relatively quick. Here's the same exact concept. Laplace transform is defined through an improper integral. But you are actually not going to be using this improper integral at all. What we're going to be doing is we're going to try to develop a whole bunch of formulas of Laplace transform, and then we're going to try to use that to help us solve differential equation without actually going through any integration or even differentiation. That's the basic concept of Laplace transform. It literally avoids everything calculus and just simply reduce the process of solving a differential equation into just basic algebra with no calculus involved, meaning no derivative and no integral involved. And that's the basic idea of it. Now, I'll show you how that works. So first thing we probably want to do is let's talk about some of the properties of this Laplace transform, or rather some formulas that we're going to be using. So here's where we're going to start. Maybe we'll define some properties of Laplace transform, and there are quite a lot of them, and we're going to start with a small list, and then eventually we're going to create a big table for them. And as a matter of fact, if you look at Google Classroom, I actually posted a ditto with a whole bunch of Laplace transform formula that you would need when you're taking a test. That formula sheet you'll be allowed to use that formula sheet when you're taking a test. I don't expect you to memorize all those formulas, but you do need to know how to use them. So here are some important properties of Laplace transform that we'll need in solving differential equation. So some of these you do need to memorize, and some of these you notice that they are actually on the formula sheet that I gave. So if it's not on the formula sheet but you need to know, then you're going to have to memorize it. And I'll point out which one that you need to know. So the first one is probably this one. The first property is that what happens if I put in a exponential function e to the at? What is that equal to? So based on the definition, is actually equal to this. So now the question is, what is this improper integral actually equal to? So actually pretty simple. So what we're going to do is we're going to try to figure it out. So that basically just equal to this, equal to integral from 0 to infinity e to the a minus st dt. And according to the integration of e to the some constant t, that just basically equal to 1 over a minus s e to a minus s times t, the value from 0 to infinity. And yes, I know I'm probably supposed to put a limit as b approaches infinity to make it look nice. So maybe I do that. So therefore it's equal to limit as b approaches infinity, 1 over a minus s e to a minus s t, the value from 0 to b. So therefore just limit b approaches infinity, 1 over a minus s e to the a minus s times b minus 1 over a minus s e to the a minus s times 0, which is 0. So therefore, this thing actually come out to be this. So now comes the big question. What happened when I plug in infinity? Well, two things happen. It all depends on what happened to a minus s. The reason why, because if a minus s result in a positive number, then that would mean that when I plug in infinity for b, I would have e equal to positive infinity, and therefore result in this thing go off to infinity. So here are two cases to consider. First case, if a minus s is greater than 0, then e to a minus s times, well then, limits as b approaches infinity, e to a minus s times b would approaches infinity. And this improper integral diverges. Now, of course, here's the problem. The problem is that in order for us to define the Laplace transform of this function, we need this improper integral to converge. So how do I make it converge? Well, it will be case 2. Case 2, if a minus s is less than 0, or what I'm going to write is s minus a to be greater than 0, then limit as b approaches infinity, e to the a minus s times b would then instead approaches 0, because when you have a negative number in front of b, this becomes e to negative infinity, and e to negative infinity becomes 0. And therefore, it converges to what? To negative 1 over a minus s, which I can then say that's the same thing as 1 over s minus a. So therefore, if the Laplace transform exists, then we know the following. If I take the Laplace transform of e to at of s, that's just equal to integral from 0 to infinity e to negative st times e to the at dt, and that's equal to 1 over s minus a, as long as s minus a have to be greater than 0. So that's our first Laplace transform formula that you need to know. Give you some example on how to use this. What is the Laplace transform of e to the t of s? So instead of going through the improper integral and try to evaluate, now we can just simply use the formula. So in this case, compare this expression to the formula directly on top, I can identify that a must be 1. So therefore, this Laplace transform tells me that that must equal to 1 over s minus 1. Give you an example. What if we have this? What if I have Laplace transform of e to negative t? Well, that would mean that when I compare that to the formula, that would mean that I have a negative 1 as a. So therefore, that must equal to 1 over s plus 1. And of course, e to the at is just a very basic function that we started with. We eventually go talk about Laplace transform of other function. Then we have some other formula that we can use so that we don't have to go through this process of using improper integral to do it. Now, that's our first property, which allows us to know what happened when I plug in an exponential function and what's the Laplace transform of that. 2, since differential equation involve derivative, so we're going to have to know what happened when I do a Laplace transform of a derivative of a function. So let's try to figure it out. The second one that we're going to do is this one. Is what happened if we try to do a Laplace transform of some unknown function derivative of it. Laplace transform of f prime of s. So how will we figure that one out? So to figure this out, we're going to basically do the same thing just like before. We're going to try to go through the integral and see if we can somehow find a formula for this. So therefore, it will be basically integral from 0 to infinity, e to negative st, f prime of t dt. So I'm going to have to basically integrate this thing. So how am I going to integrate this? Well, it's simple. You do integration by parts. So let's go through the process. So I'm going to go and do my integration by parts right here. So in this case, we have u du v dv. So how are we going to set up our integration by part? Well, pretty simple. In this case, we don't know what f is. So we also don't know what f prime is. But we want to avoid keep on taking a derivative of this thing. So what I'm going to do is I'm going to basically put f prime of t dt as dv. And u will be e to the negative st then. And so what's the derivative of e to s negative st? That would be negative s e to the negative st. The integral of f prime of t dt will be just f of t. So now I'm going to go and put my integration by parts. So therefore it will be e to negative st f of t minus integral of negative s e to st f of t dt. Yep, I forgot dt here. dt. There you go. So let's clean up this thing a little bit, but I do need to evaluate this from 0 to infinity. So we're going to deal with that in a little bit. So let's clean up this mess a little bit. So that will be e to negative st f of t, evaluate from 0 to infinity. Notice there's a double negative, so we'll send plus. S, in this case, a constant because we are integrating with dt. So we're going to pull out s, integral of e to st f of t dt from 0 to infinity. Oh, I forgot the negative. There you go, negative. So you might be thinking, like, how do we figure this out? Look like this is another integral right here, right? And you're correct. There is another integral right here, e to negative st f of t dt, integral from 0 to infinity. But if you think about it, I actually know what that is. Because that integral from 0 to infinity, e to st f of t, we actually define that to be the Laplace transform for f. So therefore, meaning that this thing right here is actually just L of f of s. And therefore, I'm going to bring down the s and keep the plus sign. Now comes the big question. What happened to the front? Well, I don't know, but let's plug it in and see. So therefore the front would equal to e to negative s times infinity, f times infinity, minus, plug in 0, e to negative s times 0 would just be 1, and I just have f of 0. Now, here comes the important part is I don't know what e to negative s times infinity, e to negative s times infinity times f of infinity will look like. But seem to me that I can reasonably assume that e to negative s times infinity would become 0. And the function f might go off to infinity, but we can assume that it might not go off to infinity faster than the exponential function. And if that's the case, then we can assume this to be 0. Because we have an exponential function that approaches 0 extremely fast. So therefore, it's not unreasonable to assume that when I multiply that to some function, even though it might go to infinity, it's probably not going to be fast enough to compare to exponential function. And if that's the case, now we have a formula. Our formula is this. So now we have our second formula. That tells us what happened when I take the Laplace transform of a derivative of a function, f prime. That would equal to negative f of 0 plus, oops, missing an s times L of the Laplace transform of f. And this, we have to assume the limit as t approaches infinity, e to negative st f of t is equal to 0. Now, of course, you might be wondering, like, okay, so we do have all these assumptions that we have to work with. Do we have to worry about them? My answer to your to that question is no. We go always assume these assumptions are true for all the problems that we're going to be doing. So that way you don't have to worry about constantly checking those assumptions. Maybe I prove one more properties, and then that will be it for today's video. So the third property is extremely important. The reason why, because it's directly related to how we can actually be able to use Laplace transform to actually solve problem. And that's the following. Let's say we're going to say let the Laplace transform of f of s is equal to the integral from 0 to infinity e to negative st f of t dt. So that's the Laplace transform for f. And let's say we have a second Laplace transform for the function g. And so that's equal to basically the same exact improper integral, except we have g in front. Now comes the big question. What if I take the Laplace transform of some constant alpha multiplied by f plus some other constant beta multiplied by g? What would happen to this thing? And some of you might already figure out that what I'm trying to prove right now is to try to prove that Laplace transform is a linear operation. And it shouldn't come as a surprise that I want to do that, because remember, when an operator is linear, it makes it a lot easier for us to actually use it to solve a differential equation. Okay, that's the reason why we prove that differential operators are linear, so that we can actually make use of linear algebra to help us figure out what the solution is. So here's the same exact concept. I'm trying to figure out that if Laplace transform is linear or not. And spoiler alert, it is. So I just want to show you why it is. So if I do that, then therefore it would imply that I'm defining the improper integrals, integral from 0 to infinity, e to negative st, multiplied by alpha f of t plus beta g of t dt. Now, because this is inside the integral, I'm going to go and do the following. The first thing I'm going to do is I'm going to go and multiply out e to st. So it become alpha e to negative st f of t plus beta, e to negative st g of t dt. Since now I have a sum between two functions inside an integral, I can now separate these two integrals. And then pull out the integral, pull out the constant. And then notice, now we end up with two improper integrals that basically represent the Laplace transform of the two functions. And therefore allow us to show that in this case, and using this proof, we can now show that the Laplace transform is actually a linear operator. That changes a function to another function. Okay, remember we use the term operator to usually refer to something that work on functions, not on numbers. All right, I think we'll stop right here. We did do a lot of math already, and don't be alarmed if you're not sure how Laplace transform is going to help solving differential equation. That will be what the later video is going to talk about. Also, don't worry too much about the improper integral. What we're going to be doing is to try to find more formulas that will allow us to basically transform a given function into its Laplace transform of that function directly without go through evaluating the improper integral. So don't worry too much about it if that confuses you, but do try to pay attention to whenever I give you some formulas. All right, so I think we'll stop right here and we'll continue some more in the next video. Okay, talk to you guys soon. Bye bye.